We're supposed to use derivative tests to find local extrema. So the derivative test means you take a derivative, you set it equal to 0, and wherever the function equals 0 or fails to exist, those are all the critical points. Those are all the potential maxes or mins. So to take a derivative, let's rewrite it a little bit. This is the same thing. Because the square root means it's a 1/2 power, and 1 over something to the 1/2 power, we can make it be a negative power by moving it upstairs, but the whole reason we move it upstairs is so that we can use the power rule with differentiation. Okay, because now the derivative is pretty easy. You could do it with the quotient rule. I think the power rule is just a little easier. The negative 1/2 comes down and multiplies. The power gets reduced by 1. And then we take a derivative of the innermost function. So the derivative of 54x minus 27x squared, that's 54 minus 54x. Okay, so that's our derivative. Now we need to set it equal to 0 to find all the critical points. And I'm actually going to move this back downstairs. We still have 54 minus 54x in the numerator. And in the denominator, you've got 54x minus 27x squared all to the 3/2 power. Okay, and now when we try to find critical points, the first thing we should always do is find out where the derivative fails to exist. So since this is the derivative, it would fail to exist if we have divide by 0 error. So we want to set the derivative equal to 0. The denominator equal to 0. Different D word. Okay, so we set the denominator equal to 0. And then this is quadratic, so we can factor it. We can factor out a 27x. And we're left with 2 minus x equals 0. And then solving each factor piece, setting it equal to 0, get x equals 0 and x equals 2 as critical points. And then the other critical points would be where you solve this. So we could multiply both sides by -2, which gets rid of that. And then we want to multiply both sides by the denominator to make this cancel out. So that's gone. So we're left with 0 equals 54 minus 54x. And then if you solve that by setting it equal to getting x by itself, you should get x equals 1. So 3 potential critical points. Okay, and this is where you'd want to test using the you could find a derivative and use your positive negative signs. But a quicker way of doing this would be to look at it and seeing that it's multiple choice. We already found x equals 1 is a critical point, and they're saying this is one of the correct answers. It's either a local min or a local max. So to find out which is which, we could just visualize this real quick with a number line. Here's x equals 1. We want to know what the y value is so we can get the question right. And the y value comes from plugging 1 back into the original function. So if you plug 1 into the denominator, you get 54 minus 27. And then if you take a square root, and then it's 1 divided by that answer, so we get 0.192. So let's forget about this one, let's forget about this one. It's either of these two. It's either local max or local min. And so to figure out whether it's a local max or local min, 0.192. Test a point to the left or to the right. 0 seems like it'd be easiest. No, but we can't divide by 0, so we can't do that. Let's plug in x equals 2 and see what the corresponding y value is. If it's below this one, then we know this has to be a max, right? So if I plug in 2 into the function, 2 squared times 27, and then 54 times 2. Oh boy, I picked another one that's undefined. Okay, so y equals 2 also didn't work. I got to plug something in a little closer, something that's actually in the domain. So if I plug in 1.5 into this function, I've got 1.5 squared times 27, and then 54 times 1.5 subtracted by that answer. Then take the square root, and so 1 divided by that. So if I plugged in 1.5, I got 0.222. That means an x value slightly to the right has a higher y value, so this must be a local minimum.